You guys are witnessing history right now. That's because this is my first bonus video on this channel. Now, for those of you who are following my channel and are looking at my series, you might have noticed that multiple times in my videos I said this will not be calc based and I will do another calc based series video in the future. And well, that is absolutely right. I did really want to add just a bonus video about work, energy, and power, which is a little bit of calc based, and this will just serve as a short introduction video in order to just get a deeper understanding if you know calculus. Now, when my calculus-based physics series actually comes from mechanics, and I actually start showing all this stuff, there will be more derivations, more proofs, and more difficult things to do. But this is just a short introduction that I want to show in order to help you guys have a deeper understanding. So let's move on to the video. Alright, so we have this thing where it says calc based, and we are going to use calculus from the very start. You might have noticed in my work video, I gave a definition of force times distance, or force times distance times cosine theta, as a slightly more general formula. But what happens when that force is not constant? Because this is assuming that force is constant, and that's not always true. Force is pretty much never completely constant. It's always changing. Think about when you're playing a sport or anything. You're not going to be running at the exact same speed for a very long time. Your speed is going to change. You're going to speed up, you're going to slow down, you're going to do a lot of things. You're going to change direction. So, for that, we need something more general. And that's where our good friend calculus comes in. Calculus says, who needs that definition? Let's add an integral onto this. So we have our force, this integral over a path, but that's not necessary. That will be talked about in my actual calculus series. All you need to know for now is it's force times d times r, which is pretty much the distance that we use. And we're not using actual d for distance because that would look a little confusing. So that's why we use f times dr. But this is the integral. That's saying, let's say we have a coordinate plane like this, and we'll draw our force vector and stuff. So over here. Now we have our force vector facing this direction for an infinitely small distance r. Now that is where this comes from. Instead of doing differentiation with time where we do very small intervals of time, we integrate it by distance. So this is at this magnitude and this direction for this infinitely small distance. And then, let's say it changes. Let's say it goes here for the next r, then here, then here, then here. All of these across this infinitely small distances r. And when you calculate all of that, then you get the total work. And that's why this formula is so effective. And if the force is constant and the distance is given, we can just integrate it and we get FD cosine theta. And it's really that simple. Now, another thing you might be confused about of where FD cosine theta comes from, which involves vector algebra, which also I'm trying to refrain from using that much vector algebra, or at least very little vectors in this series. And when we go into calc-based physics, I will use more vectors as they are more foundational and stuff. But for now, you don't really have to worry about that. Just know this is why it is this integral over here. Now, then, what we have is energy. And if you saw my video about the work energy theorem, you saw that the work is the change in kinetic energy. Now, this theorem doesn't really prove what kinetic energy is essentially directly. But what it does do is this sets up a very important relationship that will be used in the last step of the proof. But in order to prove this, we will have to use our good old definition of work that we saw over here. Our work is equal to the integral of f times dr. Now, what we're going to do is we're going to differentiate both sides. So, differential of work. Now, you could divide by dr, but we are not going to right now. So, differential of work is then force times the differential of r. Now, this force by Newton's second law is equal to mass times acceleration times this dr. Now, acceleration is equal to the derivative of velocity. So dv by dt times dr. Now, if you learned calculus, you know that these differentials aren't exactly like fractions, and you can't manipulate them like fractions. But what we are going to do is we are going to manipulate them by fractions. And yes, I know this sounds very surprising, but this essentially just comes down to using the chain rule, dr over dt multiplied by dv. Now, by the chain rule, you can get dv by dt is equal to dv by dr times dr by dt. And I showed you in my chain rule 1 how that works. But then when you have multiplied by dr over here, you see what you have over here is you have dr by dt, which is our velocity, and dv by dr, so the differential of v over the differential of r, but then you multiply it by those differentials of r, and that's just like integrating the derivative. So then that essentially means we can cancel in quotations out, but in reality all we're doing is just taking the integral essentially of the derivative. So we get v dv, and that's what this equation is going to use. M times v times dv. And don't worry, it will be covered more in depth in my actual calculus-based physics series or mechanics series, which will come after this more algebra-based mechanics series. So there you have it over there. And now what we can do essentially is we can integrate. It's really as simple as that. So we have the work, integrating the work, then we get mass. Since mass is a constant, we go on the outside. Then we integrate v dv, so m just becomes mv squared by 2 plus c. But we're looking for the change in kinetic energy. Oh, I got you there. I told you that this work energy theorem would come in handy in a little bit, and there we go. Because now the change in kinetic energy is this change in these velocities. And then, so mvif minus vi squared, because really we're going to be taking the definite integral of this from vi to vf. Sorry if I didn't mention that, but it was not completely necessary. Squared over 2. So removing the change element, you get the kinetic energy is mv squared by 2, and that's the actual formula for kinetic energy. And there you go. That's the proof that kinetic energy is equal to mv squared by 2. Done relatively simply, actually, through calculus. If one were to use algebra for this proof, it's still possible, but it would take a couple more steps and a couple more identities. But for this, all it required was a solid understanding of differentials and calculus and our handy work formula. But I defined kinetic energy? What about the potential energy that we were talking about in our work and energy video and our conservation of energy video? Well, I already did a mini derivation in that video. But if you didn't see it, you can realize that it's just since our weight is mass times gravitation, which is our force, and since work is equal to change in kinetic energy, that means work and energy are pretty much the same thing, and that's what this work energy theorem has been trying to get at. So to find kinetic energy, you just find the work. So that work is just times distance. So mg distance, or just mgh, and that's what our potential energy is equal to. So that is much relatively simpler compared to kinetic energy, but I do feel like the kinetic energy one is still pretty satisfying and very important for people to know, especially if they're doing calc-based physics. But you noticed here, we only covered 2 out of the 3 terms. We covered work, we covered energy, but what about power? So let's start covering power. What is power? Well, power is technically force times velocity, or work over time. But this is just the average power. Just like that work was dependent on that force and the average force over that distance, power is again dependent on this. But forces are not always constant, and work is not always constant. So, how are we going to do power? Well, let's say we are going to be taking this work on these small intervals of time represented by these arrows. The distance is an infinitely small unit of time called dt. So, since that little change in work over that time happens, we get power is equal to the change in work over the change in time, and that's essentially what our power is. And another way to write that would be dw is equal to p dt, and from there you can even prove that power is equal to force times velocity using the fact that this over here, dw, is also equal to m times dr by dt times dv, and solving from there. So it is very, very, very interesting to see how this all relates and connects together, and I feel like it is very important to know how power is connected to the rest of these. So there's that, and let's continue the derivation of this. And over here, what we have is this, our dw. So p, reverting it back to a slightly earlier form, we get p is equal to, or p dt is equal to force times dv, and then integrating both sides gets us power is equal to force times velocity. And it's really that simple. And actually, I have another derivation for that. Since power is equal to dw over dt, power is equal to force times, if force is constant, then we get force times dr over dt, and that's velocity. So when it's constant, it's also equal to force times velocity. And it really is that simple, the force vector at the time times velocity. So I know this video is not exactly in the subject realm what we were doing. We were focusing on a lot of problem solving and algebra-based physics, but I think once in a while I will be adding these different bonus videos, going a little more in depth about these topics, but not to the level of my future up-and-coming calculus-based physics course, where I talk about all of this stuff in more detail. But I really do think it's important to understand how all of these things, all of these formulas and stuff, which look so random at first, actually are very, very connected to calculus. So, if you enjoyed this video or found it helpful in any way, please make sure to like, subscribe, and hit that notification for more awesome videos just like this. So, see you in the next one. Thank you so much for watching this video. You guys really are the best part of what I do. See you in the next one, and bye-bye.